Presented by Caltech.
And normal modes together make standing waves. Again, you can add up these normal modes for a generic solution. We also discussed that. We spoke about the Fourier decompositions. So when you have these boundary conditions and normal modes, they feed into Fourier decompositions. And very, very important, any function could be decomposed into a bunch of sines and cosines subject to boundary conditions. If you have fixed, it will be a sine series. If you have fixed open, more stuff could happen, and so on and so forth. And from here, then we ventured into the fact, how could we add these waves up together? Could we just have one wave? If we have multiple waves, what do we do? Then we spoke about interference. We spoke about diffraction. And so on and so forth. Okay? So this kind of like sums it up, the last 10 weeks in the last 3 minutes. So hopefully you have a sense of what we did overall in this course. I know this review, people wanted to be more about the final exam. We talk about problems. But I want to appreciate from where we started off and where we ended. Because we lose sight very often of what the underlying dynamics is. So starting with a simple harmonic motion, like F equals minus kx, from that basic idea, developing it up, we understood how earthquakes work, we understood how Fourier decompositions work, we understood how mathematical problems could be solved with this, a whole bunch of scenarios came out of this whole idea. Okay? Any questions about anything broad in the course? Just go to the examples. Examples? All right, I see the nods. Okay, and also before I go to the examples, a couple of announcements. I should have mentioned this before. So the exam will come out on Friday, and do not submit your exams in the physical box outside 201 East Bridge. It has to be done electronically on this platform called Gradescope. I'll send an email out to everyone today about what Gradescope is all about, but please submit it on Gradescope, both your individual and your final and your group exams. Other than that, Friday I'm not teaching. So this is my last recitation for the term. And also I will be incommunicado for the next 2 days. I'm flying back to India, so it will be a 30-hour trip. I'll try and be in touch, but for the next 2 days, there'll be no email contact mostly. So if you email me, expect to hear back Friday afternoon, Friday night. Okay. Examples. Let's start with the coupled oscillations part. I mean, you kind of understand how the damped and the basic parts work. Let's figure out how coupled oscillations again. A quick example. So think of the following system. Say you have a frictionless surface. Again, ideal situation, it's nice and good. Say you have a spring, okay? And there's a mass line of capital M mass on the table. And I somehow am able to arrange for the fact that I can hang a pendulum from this mass. I'm smart, I can do that. So this is where the mass M, there's a pendulum which hangs from this mass. Okay? And I'm trying to look for the normal modes of this particular system. Whenever you're given a system, where do you start? There's a way of thinking, please keep prompting me like how to go about this. I've done stuff like this before. It's not new stuff. It's more about you folks coming up with, I know this, I know that, and I'm making a whole sense of what's going on. So if I'm given a system like this, spring constant K, maybe, yeah. So where do we start? What's the first step? The equations of motion. Excellent. You just have to perturb the system a little bit and see how it responds to those forces. In this location, it's in equilibrium. It's not moving. Okay? You try and displace it by a small amount. When I do that, let's make the drawing again. So you extend the spring a little bit. That's mass M here. So this is the equilibrium position, let's say. So this thing went up by, for example, x1. Okay? And I also perturb the pendulum by a small displacement. Let's call this angle theta. And let's call the net displacement of the second particle, little m, from equilibrium as x2. again, you make that configuration. It's some configuration for some variable x1, x2 and corresponding theta. Okay, you perturbed it over the equilibrium. Once you have that, make all the forces. What are the forces? There's a table. Let's not forget that. Mass 1. What forces are there? Gravity, normal. But I'm mostly looking for motion along the x direction. Okay? So the spring force, which acts on the mass, points again in the negative x. This is kx pointing this way. Kx1. Okay? What are the forces? What about the second mass? It has some gravity. That's good. That's mg. What else? There's the strings. There's a tension force acting on this mass. There's a tension here. The string is inextendable. It's an ideal string. The same tension holds everywhere. Therefore, the tension also tugs on the mass, capital M, from top. Okay. And I'm looking only at the x motion of this whole system because that's my plane of interest, basically. Do we agree that this is a coupled system of equations? Right? How mass 1 moves depends on where mass 2 is because of the string joining the two, and vice versa. Okay? So let's write down the two equations of motion. So capital M x1 double dot is something, and little m x2 double dot is something. For the first mass, what are the forces along the x? There's a spring force on the negative side, so that's minus kx1. What else? The tension forces, horizontal component. So this angle is theta. What's the component in the horizontal side? Cosine or sine? Sine. The cosine is the vertical one. Cosine is the horizontal one. It's in the positive direction by convention here in the figure. So it's t sine theta. What about the horizontal force on the second particle? The x direction force. Does gravity have an x component? No. What has? Tension. If this angle is theta, so is this. So what's the horizontal component of theta of t here? Cos or sine? Sine again. And the negative side. So you have minus t. Okay. Now again, you wrote down variables, you guessed a few variables around. It's pretty inhomogeneous. You have x's, you have thetas, it looks ugly. Try and write down thetas in terms of the x's. You want to have an equation of motion which writes down double dots for x1 and x2 in terms of x1 and x2, and linearly preferably. Okay? So again, at this stage, make free use of the small angle approximation. Make angles small. Okay? So what's sine theta? This is a combination of geometry and of Newton's law. That's it. Write the forces down, make the geometry, write the forces. What's sine theta in terms of x1 and x2? Given that the length of the string is, let's say, L. Looking at the sine of this angle, x2 minus x1 divided by L. You'll see it? So sine theta is x2 minus x1 divided by L. Now here it turned out that I didn't have to use a small angle approximation. Even for large enough angles, sine theta is linear in x2 minus x1. I can just directly put this back in my equations of motion. Okay? So what do I have? I have the first one as minus k x1 plus t x2 minus x1 divided by L. And the second one is minus t x2 minus x1 divided by L. Okay? Okay, so that's that. So I have x1 double dot equals something and x2 double dot equals something. Again, write them down as a linear combination of x1 and x2. Okay. So for the first one, I have a term minus k and a minus t over L from the x1 part. So I have minus k over m plus t over ml, okay, times x1, and I have plus t over ml x2. That's the canonical form of things. You want to always have equations of motion as a linear combination of the original variables. Okay? The second one looks more simple. This is T over, this is capital M, sorry. So this is the first mass, this is capital M. Second mass is T over little m, L, x1 minus T over m, L, x2. Do we all see that? Is that okay, everyone? If there are questions, please ask me. I can imagine this might look easy to some, hard to some, that's fine. But if we have questions, feel free to stop me anywhere. Can I connect the tension with the mass of the second object? Now this thing is not moving much in the vertical thing. For small angles, now for small angles, it's mostly moving horizontally. Okay. So for small angles, I can, balance the force in the y direction, and therefore I'll have T equals mg cos theta. Okay. And for small angles, T is approximately mg to first order. The correction in the cosine is higher order, it's the second order in the correction. So T is approximately mg for small angles. This thing is exact. If I make approximations for small angles, then I can replace T with mg only when the angle is small. Okay? Because cos has like 1 minus theta squared, and we want linear equations here. Okay? Once you have this, have them right there and have a matrix form for the equations. So I have x1 double dot, x2 double dot. Can like start picking up speed a little bit here. So you have minus k over capital M plus t over ml, t over ml, t over ml, minus t over ml times x1, x2. Okay. If you want a more conventional form, I can pull the minus sign out from this 2 by 2 matrix. Right? We call that minus m, the whole thing in class before. So you have this. And what was the whole deal? If I write this down as a matrix minus m times x1, x2, you can find the eigenvectors, find the eigenvalues of this matrix m. And those eigenvalues are the normal mode frequency squares. Their omega squares are the eigenvalues of this matrix m. Yes?
On the bottom, the m should be lowercase.
Yes, thank you. Yep, so this is little m, this is little m, let's call this matrix m tilde. That's the 2 by 2 with the minus sign out, and omega squares are the eigenvalues of this matrix. Okay, you are okay with that? I think the hardest part people find is that like, how do we start this question? I think once you're here, it might be a little more tractable. Are people okay with getting eigenvalues, eigenvectors question?
Why do you have to pull the minus sign out?
Because just by convention.
Oh, okay.
So that omega squares are the eigenvalues of m tilde. You could have found the eigenvalues of this. Those would have been minus on this class. So just yes. Yes. So out here, my equations are completely exact. Right? Sine thetas are exactly x minus 1 over L. These are my exact equations of motion. Okay. So are these. But the tension is an unknown for us. Okay. So the tension is mg cos theta, and the particle is only moving along the x direction. Yes, of course, it has some y displacement, but for small angles, it's mg cosine theta, right? And again, for small angles, this is approximately mg. Because cosine theta is 1 minus theta square over 2 factorial, yada, yada, yada. For small angles, I can drop this part, so approximately 1. Yes?
What if the subbing of cos theta is geometrically?
We can just make things harder.
Okay.
Because if you can imagine, if I make tension in terms of cos thetas, how much is cos theta? Cos theta is the cos component of the length and so on and so forth. That will become higher order because it's multiplying with the x's again. And something with the x will make it higher order. So you want to keep it in there.
Okay.
So first, tension depends on where you are in this whole system. But for small angles, tension is approximately constant. And then this whole matrix becomes a constant. You see what I'm saying? Okay. So build it up. Don't like jump the gun and try and get to this equation directly. Perturb the system, get the equations of motion, and go from there. Yes?
What would you do if like sine theta was not exact?
So I mean, this is just because this is geometry, right? I mean, that's the case. You could always find equations of motion, but let's say there was like, let me say this way. If you write down equations of motion of an angle, for instance, so if you have like, let's say, m theta double dot for one variable for a model. So this is minus, let's say, k times sine theta. So this is the variable and the variable here itself. Then for small angles, I can approximate this as k theta. Okay? Out here, I was just able to directly use my relationship of the thetas in terms of the x's to work my linear relationship out. But if my angles were involved, and then there was a sine, I could just do this small angle approximation for the sine itself. Does that make sense? Any other questions? All with me? Okay. And again, if you want to find out the normal modes, what do? You make an ansatz. You say the fact that my normal modes are the two particles, x1, x2. They can have some amplitudes, a1, a2, could be complex at this stage, e to the I omega t. They both have the same frequency of oscillation. You plug it back. That's tautological to saying that omega squares are the eigenvalues of the matrix M tilde. Solve for them. General solutions are sum of the two normal modes. Okay? All okay with that? Make sense? Okay. Then I want to talk about a little bit about, let's see, Fourier decompositions. Those are important.
There's a question.
Yes.
Sorry, I missed. What is A1 and what is A2?
So this is an ansatz. If I want to find out my normal modes, what do? You make a guess for my equations of motion. They are those solutions normal modes for which both the particles have the same frequency of oscillation. They could have some amplitudes, right, which are unknowns. These are the eigenvectors that you would find out. So you take this whole ansatz in, you plug it back into the equation of motion. From there you find out omegas, and then you find the A1s and A2s, and then you just add them up together to the whole solution. Is that okay with everyone? I'm guessing it's okay with everyone, hopefully. If you have questions, please ask me. Yes.
So like both particles have the same equation or same frequency omega, right? Okay.
For the normal mode.
Okay.
That's how you define the normal mode, right? It's all the n particles, they all have the same frequency of oscillation. Okay. So that's like coupled oscillations. You know where to start. Once you have the starting point, then kind of like makes sense like how to continue from there. Okay? Alright. I just want to kind of review the Fourier stuff a little bit in a little more detail. Now once I have a continuum limit of like n particles all joined together, it's a wave equation. So I have my wave equation, partial square y, partial c square, this is speed square, partial square y, partial x square. Okay. Again, how do you find the normal modes? If you're stuck, just start there. That's the starting point for all these things. So I have a string in the x direction, 0 and L, that's the endpoints. The string is doing something between these two locations. That's my variable y. How do you look for normal modes? A normal mode again is a special solution for which all the n particles, which are now labeled by the location x, they all have the same frequency of oscillation. Okay? So every particle on the string has the same frequency, e to the I omega t. That's the oscillation part. And the amplitudes could depend on where I am. Okay? If you don't know where to start, this is where you start. Call it a separable solution. I have separated out my space and time components into two distinct parts. Use that. From there, you start into the whole thing, and then you have fun. Okay? You plug it back in, you solve for these normal modes. And as we solve, they come out to be, these normal modes come out to be is sum A sine kx plus B cos kx times C cos omega t plus D sine omega t. How are omega and k connected? What connects the frequency omega to the wave number k? the velocity. At least for the physics 2A wave equation, the dispersion relation is what generically connects omega to k. And for this wave equation, we have omega equals Ek. Okay? So k is just omega over v. So as long as you specify either omega or k, you specify the normal mode. So normal modes are labeled here by the frequency, as they always are, or by the corresponding wave number. Yes.
So all this derivation in like the Fourier discussion is only if it's bound at both ends.
No, doesn't have to be.
Okay.
By bounded, you mean like fixed, or you
Like
mean
fixed
just
at both ends, yeah.
no? So this discussion is true for any boundary condition.
But the derivation we did for the before that was for fixed
No.
at both.
So when you start with the wave equation,
Okay.
getting a normal mode has nothing to do with boundary conditions.
Right.
Normal mode is just talking about all the n particles having the same frequency of oscillation. Right? So this string could have looked like, you know what I mean?
Mm-hmm.
Any particular shape, anywhere. But it's constrained to be between 0 and L. It can't go beyond 0 and L, that's the length is fixed, but every particle could move, at least for the normal mode. Okay? They all have the same frequency of oscillation. So this labels a normal mode, but then you have boundary conditions. Okay? Then you try and impose boundary conditions. And when you do that, so when you have normal modes again, normal modes plus boundary conditions is what makes standing waves. So once I have a particular normal mode labeled by a particular frequency or wave number, then depending on how I physically restrict my boundaries, that would change the whole idea. Okay? How about if it's fixed on the left end? What happens then? By this point, hopefully we should be able to see what happens and not to do it every single time. When it's fixed at the left end, so when I have y at x equals 0 for all time, if this thing is fixed, let me give you a broader picture here. After this, there'll be 4 conditions in your questions. There will always be 4 conditions that will be given to you. 2 boundary, 2 initial. Okay? How the string is at x equals 0 and x equals L for all times. Those are boundary conditions. And you'll have 2 conditions about the initial idea. How does the string look like? What's y x comma 0? The shape of the trend at t equals 0, and how the string moves at t equals to 0. 4 conditions can be used to simplify for the A's, the B's, C and D's, and the K's. Okay? So if I have a fixed boundary condition on the left end, what does that say? This is true for all time. When I plug in x equals 0, A sine 0 is 0. I have plus B cos 0, which is B, times a time dependent piece. So B times something time dependent equals 0 for all times. So either B is 0 or the time piece is 0. If the time piece vanishes, the whole thing vanishes, I can go back home. But that's not the point, right? Therefore B must vanish. So this implies that B. So boundary condition, fixed or constant. See, the string starts from rest. So I have, now this is the initial condition. Starting from rest means partial y, partial t, the speed of the, not the wave. This thing is not the wave speed. This is the speed of individual particles on the string. There are 2 speeds involved in the wave equation. What every particle is doing by itself, up and down, and how the whole wave, kind of traverses through the medium. So this is the speed of the string at equals 0. So I plug the string and then I just leave it. Okay. So say this was at t equals to 0. This is 0. And this is true for all x. So when I differentiate this with time, the c cos omega t term becomes minus c omega sine omega t plus d omega cos omega t after differentiation. At t equals to 0, the sine term goes away. So I have d times 1 times omega times the space dependent part equals 0, which is true for all spatial points. Therefore d must vanish. So this argument should try and come a little more naturally now. Just look at the solutions, work it out. If you want, you can also write it down step by step, you'll see it happen. Okay? So this implies that depending on the fact what my other condition looks like at x equals L. What if it's fixed at x equals L? What happens then? The b's went away already. I have a sine kx time a time dependent part. If this vanishes at x equals L, I have a sine kl time the time dependent piece equals to 0. Again, either a is 0 or the time piece is 0 or sine kl is 0. A can't be 0, everything goes away. Time piece can't be 0, everything goes away. What has to be 0 is sine kl. Hence, the k's are quantized, the k's are discretized. So in this case, if it's fixed at x equals L, for all time with boundary condition, then you have k's are n pi over L's. In case I have a free end, then the particle can move. The net force on the particle vanishes. So if it's a free end at x equals 0, then I have partial y, partial x at x equals L. This vanishes for all time. It's a massless particle on the right end. It's free to move. The net forces have to balance. The net force looks like t times sine theta of this angle. Sine theta is, you get the vertical component. For small angles, sine theta is theta. It's tan theta. Tan theta is the derivative. It's 0. And from there, you find that the k's are quantized as 2n minus 1 pi over 2. Okay. The way to think about this is whenever you have a question in front of you, identify these broad pillars. Get the boundary conditions. If they're given to you, well and good. If they're not, figure them out. Once you have them, figure out these 4 conditions. These are 3 right now. I gave the boundary, the other boundary, and the initial condition. Once you have them, the final thing which remains is the other initial condition, which tells you the shape of the wave at t equals to 0. So the shape of the wave, how it looks like as a function of x at the initial time. Someone will probably give this to you. It's a known function, okay? And then you just, from your normal modes, because a general solution is a sum of all the normal modes. Earlier, my normal modes were labeled by either k or omega, but now my k's become discretized, and hence my omegas become discretized. Why? Because if I have a kn, the corresponding omega n is just v times kn. Okay? So my general solution at t equals to 0 just becomes a sum over all the normal modes labeled by n now for some constants an sine knx, and you have the cos omega nt, which at t0 is just 1. That's what you have. From here, you can invert the whole thing by the Fourier inversion trick. So say you have a fixed boundary condition. Again, you could start here sometimes, specifically the question, or you could work your way up to see what the conditions are, how these questions hold. Okay? So if you had fixed conditions at the boundaries, kn's become n pi's over l's. And to find the ans, you just invert the Fourier relationship. That's the harder part of math. You got to do an integration there. It makes it a little tough. But if we ask you this in a final exam or a question, he would help you do it. Okay. So to find them, this is just 2 over L's, which equals 0 to L sine n pi x over L, p of x dx. Now this p of x will be a known function. Okay. You can solve for this whole thing. Once you have solved for the whole thing, you can find out y as a function of x and t, the whole oscillation, the grand finale of the whole thing, like how the thing oscillates as a function of time. You just sum over all the time-dependent normal oscillations. So ans sine n pi x over L times cosine omega nt, where omega n is kn times speed. Okay. Again, look at the question, be sure of what's going on, figure out the boundary conditions, figure out what you are given. There will always be one of these 4 given to you, or I mean, they'll all be given to you, but figure out what is being given at a particular stage of the question. Use that to either simplify the normal equations or to find out what the unknowns are. So these same ans feed into here. Okay. I could have done like a little example like by having a simple p of x, but that seems very specific. this idea is important. I mean, examples are good, but sometimes the idea is what matters. So hopefully you've seen the bird's eye view of how this really works. If there are questions about this stuff is important. I mean, if not today, if not tomorrow, if not next week, this will come up someday in your life, for sure. As engineers, scientists, even if you don't stay in STEM, do anything, Fourier decompositions do become important at some point in life, whether or not. So if you have questions, let me know.
So for that sequence, is it like always true that you are
This one? This one? No, so this depends either if the string is fixed on the right end, then you have it doesn't move, or it could be free. So it depends on what the condition is. Okay. So if it's fixed, then your standing waves look like that. That's the first standing wave. Again, if someone's confused, when I draw this first standing wave, when I draw like half a sine wave and the other envelope, it's not a fish. It's like a fish. It's not. The idea is that this is the oscillation in time. Okay? This labels this upper thing is like sine k and x for n equals 1. And the cos omega t term is what goes takes up and down. N equals 1, then you have n equals 2. And so on and so forth. That's the fixed condition. If you have open conditions on the other side, then you have the first thing looks open. Again, if you notice, partial y, partial x has to vanish at the boundary for the open condition. Just look at how this goes. The derivative vanishes of the x dependence. The second normal mode is, again, the derivative vanishes. So you always fix imposing the boundary conditions, and those fix the allowed wavelengths, those fix the allowed frequencies, and those fix on how the things look like at that location. Does that answer your question? Say it again.
What is dy dx like?
So this is because if it's a free end, the net force on the particle has to vanish. Okay, so if I have a string on the right end, the net force on this particle has to go away. It's a free particle, so it's a massless point. The net forces have to balance out. So if I have this particle at the end of the world, at the last point, and other particle, the penultimate one, they have a string connecting them. Now I've zoomed in very closely, so the string looks like discrete points. There is tension in the string. I'm looking for transverse motion of each particle. So I'm looking for this angle is theta. My transverse force Fy, which pulls it up and down, is like d sine theta. Okay. For small angles, this is approximately d theta. It's also approximately t tangent theta. Okay? Because for small angles, if I draw these curves, sine curves look like that. Linear curve for small x's looks almost the same as the sine, and the tangent curve also for small x's looks pretty much the same. Okay? If you like really zoom in into the coincide and have a look, that's what you will see. And then you have tan theta. Tangent theta is the derivative of the curve. So this is t partial y partial x at x equals L. And if the force has to vanish, the tension can't be 0, so therefore the derivative goes away in the free end. Okay? Any questions about boundary conditions, standing waves, Fourier decompositions, Fourier inversion, anything? All with me? Make sense? Question? Alright, so let's finally go into the array of interference. So we discussed 2 slits in class, right? The double slit experiment. Let's do 4 slits now. Like, why would you do that? So let's say I have 4 slits. 2, that's the center line, another slit, and another slit. Okay, and there's a stream. For these kinds of questions, always identify the paths. Get the path of individual light rays. get the path differences, and then add them up. I mean, not the path differences, add the waves, okay? What you gotta do is start step by step again. Start drawing stuff, okay? If you don't know what the final answer might look like, draw light rays, okay? Because once you have them drawn, geometrically, you can look at what the path differences are. And that is what will matter to give you an interference pattern on the screen. Be it a screen, be it diffraction grading, be it anything, okay? So let me label some things here. Let's call the first slit is at a distance, let's say D, from the middle line, up and down, those are the first two slits. And the upper one is distance A from center line, and distance A here, okay? And 4 slits. So now I send in some radiation from the left-hand side of some wavelength lambda. Again, let's remember, if you have a point source, how do the wavefronts look like? Spherical. If it's 2 dimensional, then they're circles. If it's a point in 3 dimensions, then they emit as spheres. Okay? So a point source has spherical wavefronts. What about a line source? Cylindrical wavefronts. What about a planar source? Plane wavefronts, right? The thing is extended as long as it could be, the wavefronts are planar. Okay? But the beauty is that if I take a spherical wavefront or a cylindrical wavefront, the point that I'm driving home here is that point sources are, of course, most natural in the real world. They're like localized. Line sources seem weird because they're just lines and going all the way up infinitely. Planes are even more weird. Like, how could you have an infinitely large plane? But the point being, if I have a point source which emits spherical radiation, spherical wavefronts, if I go really, really far away, and now if I look at it, how does it look like now? It's almost planar, right? So the radius of the waves becomes too large, and from my perspective, the radius is so big, I can barely perceive the curvature. I look at it as a plane wave. Same for line sources. If I have a line source, it emits cylindrical wavefronts, but very, very far away, I can approximate those wavefronts by plane waves. Is that okay? So the way these things work is that you're sending out, there's some actual source that sends radiation from far away, and now you have a planar wavefront coming in. Okay. Let's look at a point on the screen. Draw paths. So that's from the first, it's called S1, let's call this S2, S3, S4. Again, path from S1 to P, path from S2 to P, path from S3 to P, S4 to P. And let's label them R1, R2, R3, R4. I very often found that people are either not too comfortable or a little intimidated. Sometimes actually write down variables. Don't feel shy to define variables. It's all right. No one's judging you. Put whatever variables you want in the question. They will eventually end up becoming connected. Use what comes natural. In this case, I have 4 light paths. I define the distances. Okay. Once you have the distances, and say this is in the far field limit, so this distance from the slit of the screen is capital D. In the far field limit, D is much, much more than A comma B. I can neglect the cylindrical wavefronts which come out of the slits. They almost look planar here, yada, 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 the whole thing. But let's write down what the path differences are between R1, R2, R1, R3, R1, R4. So what's R2? The R2 light ray, take one as your starting point. Take R1 as your convention. That's what your zero looks like. That's what your baseline is. How much extra does R2 go over R1? And also, if someone's bothered, my bird-like looking R's and the script R are the same, so don't be bothered. If you take quantum mechanics extra, I might like change this thing, because the book has a different way of writing it, I guess, but for now, same R's. How much extra does R2 go over R1? Geometry. You have this part, you have this path. The extra path which R2 travels is this part, right? You drop a perpendicular from slit 1, so what you have. If this distance is something, then it's this times the angle that the point of the screen makes, right? So this angle is theta. for large angles. They're all thetas basically. So how much is R1 plus what? It's this distance between the two slits, this S2, S1 distance, which is A minus B. So this is A minus B times sine theta. Do we all see that? Any questions about this? This is not the most obvious thing. If you're confused, please ask me. Remember how for two slits, if you just had two slits and a screen, there's a point on the screen going this way, you drop a perpendicular. If this whole distance was d between the slits, and this angle here was theta, this is the extra path that it travels. This path was d sine theta. Same thing here. The d here is the S2, S1 distance, which is b a minus b times the sine of the angle that it makes. Okay, that's R2 in terms of R1. What's R3 in terms of R1? How much extra does R3 have to go compared to R1? Same thing, drop a perpendicular from slit 1 to the third point. Extra thing it goes is this distance here, which is exactly the distance between S1 and S3 times sine theta again. And that distance is A plus B. So this is A plus B sine theta. And finally, I should have used another board, but I'm not. So R4 is R1 plus 2A. The distance between S1 to S4, A plus A, so it's 2A. Okay. Once you have this, you found the paths. You can just add the 4 waves up. Just make up 4 waves and add them up. So the total oscillation, or let's call this E, or the electric field, or call it psi, call it whatever, at the point P is the sum of all these 4 from the 4 paths. So you have sum from I equals 1 to 4 EI, and this is sum from I equals 1 to 4, some amplitude maybe, e to the I, let me call this J, the I's become confusing, this is J, J, I, K, K, R, J minus omega t. The jth light ray travels a path Rj with a wavelength lambda, hence wave number k 2 pi over lambda minus omega t. Does omega depend on which slit I'm talking about? No. Omega is a source dependent feature. As long as I have the same source coming in, therefore the coherence of my slit experiment, if it's all coherent, they all have the same omegas. Okay, all that differs is the path lengths. What if I put on the R4, if I put a small box, or if I put a glass chamber, so this is glass now, for a distance, let's say, delta L. What happens to this equation? What changes? What should change? I mean, forget the math, like physically what should change? Between glass and air outside, what's differing for the light? I can't hear it. When light is in different media, the wavelength changes. The frequency is the same, the wavelength gets modified. Okay? So if you have lambda naught as your incoming radiation's wavelength in air or in vacuum, what's lambda glass? In terms of the refractive index of glass. The refractive index is, let's say, n. How do you get it again? Go back to the basics. The speed of the wave in a medium is speed of the light in vacuum divided by the refractive index. Okay? Omega equals b times the wave number. Omega is a source dependent feature. So omega is the same for speed in vacuum times k naught, which is the vacuum wave number, equals speed in the medium times k in glass. Okay? And this is c times 2 pi over lambda naught. V is C over N, and K glass is 2 pi over lambda glass. C's cancel off, 2 pi's cancel off, you have lambda glass equals lambda naught N. Or correspondingly, K glass is N times, no. Yeah, K glass is N times K naught. Okay. So what changed again? If once you identify this, you're pretty much done. If the K also changes, the K becomes different here for the glass portion. Break up your light ray into the path in the air, which has the wave number K naught, and a path in the glass, which has wave number K glass, and traverses the length delta L, and then work it out from there. Okay. But for now, I'm not focusing on the glass part. We're just taking a little deviation. So without the glass. You have these 4 waves, just add them up together. 4 exponentials can be summed up. And once you have the sum up, try and factorize out the net wave portion, the net traveling wave part. So if you notice, R1 plus R4 is R2 plus R3. The average paths from 1 to 4 and 2 to 3. That's what it goes through. And once you have this thing, you realize that this is a combination of 2 double slit experiments. One at a distance, the BB slits and the AA slits. Okay. And we discussed this in class in detail, like how do you add up the pattern. So don't get bothered by 4 slits, break it down to something which is more tangible, make the paths up, get the path differences so you know what the differences are. Once you have them, just get the net intensity by adding the net components, which is just kind of solving the double slit experiment twice here. So you have one from S2, S3, one from S1, S4, add them up, you have the intensity there. But I'm kind of like focusing more on the basic idea because people get stuck where to start. I think once you start off, there is enough things to hold on to do something from there. Okay. So I think I'll call it day today here. That was from my side of the review. I want to thank you all for a very wonderful term. It's been nice kind of interacting with you all. And thank you for being a good audience. I hope you enjoyed. And if people are around next term, drop a quantum mechanics to talk about how nature really, really works. So thank you so much.